Section 4.8, Lagrange multipliers. Yes, you heard me correctly. I'm saying Lagrange. Most of us will read this and think Lagrange because of the nearby town, but this is a French person's last name, so we're going to try and get it correct, just like we don't accept people saying that Euler is Euler, right? So this is Lagrange multipliers, and this is our shortcut technique for optimizing a function with a constraint. In the last section, we looked at a problem where we were optimizing a function within a certain boundary, and it was a lot of work. We had to check every edge of the boundary, and I told you there's a shortcut, and here it is. The types of problems that we will use Lagrange multipliers on are constrained maxima and minima problems. So let's take a look at an example. This problem says to find the points on the hyperbolic cylinder, that's this blue thing down here, given by the equation x squared minus z squared minus 1 equals 0. We want to pick a point on that cylinder that is closest to the origin. Can you visualize the surface? I hope so. It's already here. What we're going to do is use a sphere to represent all of the points that are the same distance from the origin. Since we want to get as close to the origin as possible, we can use a sphere to represent all of the points that are a certain distance from the origin. And then we're going to phrase the question as minimize the sphere. So we want to make the sphere as small as possible, subject to the constraint of our hyperbolic cylinder, meaning we want to make sure we pick the right sphere so that it contains points that live on this surface. Let's get an idea of what we're looking at. If we pick a sphere that's too big, we can see that it definitely contains points on the surface. We can see those where I'm drawing the white line here. So the sphere is definitely big enough. But it's a little bit too big, in fact. These points are much further from the origin than the points down here. So we picked a sphere that's too big. We're kind of going for the Goldilocks thing here. We want the sphere that's just right. If we pick a sphere that's too small, notice that it doesn't intersect with the surface at all. There's no points that are both on the sphere and on the surface. But if we pick a sphere that's perfect size, it'll touch the surface at exactly 2 points, and those are the 2 points we're looking for. The method of Lagrange multipliers will help us find those 2 points. Let me first show you how it works. We have our 2 surfaces. We have the cylinder and we have the sphere. Remember, this is the function that we are optimizing, and this is our constraint. We're going to look at level curves for each of these surfaces. Remember that level curves are where the function is a constant height. So I found a few level curves for the blue surface and graphed those here. And then for the red surface, found a few of those level curves and graphed those here. If we were to graph the level curves in the same plane, notice that there's a pair of level curves that touch each other. So one level curve from the red surface and one pair of level curves from the blue surface. They touch each other. And they happen to touch each other right at the point that we're looking for. When the sphere is a perfect size, the surface and the constraint touch at those points that we're looking for, the points that are closest to the origin. The level curves through these points are tangent to each other. They only share the same point. They don't share multiple points. Well, I guess 2 points, but at each touching, they share exactly 1 point. And you can kind of see that in this picture up here. It's touching perfectly at 1 point. Because these level curves are tangent to each other, they will have the same tangent line, and they'll have the same tangent plane, which means that the gradient vectors are parallel. So let that soak in for a minute. The gradient of this red surface, let's call that maybe gradient f. the gradient to the blue surface, let's call that gradient G. And I'm saying if these level curves are tangent to each other, then their gradient vectors have to be parallel. We know that for all parallel vectors, we can write them as scalar multiples. So if V is parallel to U, I can write V is equal to some constant times U, scalar multiples. For two vectors that are scalar multiples, we're talking about gradient F, gradient G. These guys are scalar multiples, which means we can write them as gradient F is equal to some constant. The constant we're using is lambda. It's a Greek letter. And we use that as our Lagrange multiplier. So we have gradient F is equal to lambda, the Lagrange multiplier, times gradient G. This is a simple statement that derives from the idea that the two vectors are parallel to each other. So all we have to do is use that one simple idea. Gradient F is equal to lambda gradient G, saying that these vectors are parallel. And then when we solve this system, it'll give us the x and y, maybe z if we have a three independent variable function, but it'll give us the points we're looking for. Let's try this example. So we want to find the greatest and smallest values that the function f of xy equals xy takes on this ellipse. Now, the first thing that we have to do when using the method of Lagrange multipliers is make sure that you correctly identify what is being optimized and what is the constraint. So we're looking for greatest and smallest values of this function. So greatest and smallest of this. So this is what we are optimizing. And we are only allowed to pick points that live on the ellipse. Awesome. Once we know what we're optimizing and what we are constrained by, we can get to it. We will call the thing that's being optimized the f of x, f of xy. And in this case, the function was already called f, but whatever, we're being redundant, that's fine. And then the constraint, we're going to take whatever the constraint is and rewrite it so that it looks like a function g of x and y, just like the function we're optimizing, equal to a constant. We already have that here. We have a function of x and y on the left side of our constraint equation equals 1, a constant on the right. So it's already set up the way that we need. It is important to make sure that you can take the constraint equation and rewrite it as the function equal to a constant, because without that, finding the gradient would be more difficult. So first thing, identify what you're optimizing, what the constraint is, and then label them F or G accordingly. I'm going to write that as just identify F and G for step 1. Step 2, find the gradients. Once you know what F and G are, you can find the gradients. The gradient of F, first component is the partial with respect to x. That looks like y. Second component is the partial with respect to partial with respect to y, which is x. Next, we have the gradient of G. So we need the partial with respect to x, which looks like 2x over 8, or x over 4. And then the partial with respect to y, which looks like 2y over 2, or just y. Then we can set this up using that Lagrange multiplier equation. So we're going to plug those into this equation. So gradient f was y comma x equal to lambda times gradient g, which is x over 4 comma y. And now we need to solve this for x and y. And we're going to do this really similar to how you would have solved a complex equation. So an equation that has real parts and imaginary parts. We're just going to separate the corresponding components. So on the left-hand side of the equation, we have two components. We have the x component, which is equal to y. I know that's going to make our heads spin a little bit, but that first component is the x component. It's equal to y. Then we have the y component, which is equal to x. Remember, the y component is the second component, and that has an x in it. Oh, you know what? Let's, instead of call it x component, to try and clarify it, let's call it the I hat component. And instead of the y component, we'll call it the j hat. And that might make it a little more clear. So on the left-hand side of the equation, the I component is y, the j component is x. Now we need to write the right-hand side of the equation. If I distribute this lambda in, the I hat component on the right-hand side of the equation would look like lambda times x over 4. And then if I distribute my lambda in, the j hat component looks like lambda times y. This essentially creates a system of equations that we need to solve. But notice that there are three unknowns. X, y, and lambda are all unknowns. And this is a problem because we only have two equations, which means this system is underdetermined. We need another equation, otherwise we can't solve this. So what we do is pull that constraint into the picture. So the system that we're really going to solve needs to have three equations because there are three unknowns. So we add that constraint in. As our third equation. So rather than just using the I hat component, the j hat component, we're also going to use the constraint. That way we have enough equations to balance out the number of variables that we don't know the value for. Now, one extra fact is we do not care what lambda is equal to. Lambda is a stepping stone that gets us to the answer that we want. We're looking for the x's and the y's. We're looking for the points, x comma y. Lambda is just something that's going to help us find those correct values. Sometimes we have to solve for lambda first. Sometimes we can completely bypass solving for lambda. So don't get wrapped up in what lambda is. Just use it as a tool to find x and y. All right, when it comes down to solving the system, we've got a few different tools we can use. In this case, I would like to use substitution. I would like to plug x into that first equation so I can eliminate a couple of, well, not eliminate, but we can reduce the number of variables we have. So that would look like y equals lambda times, instead of x, I'll write lambda y, since the second equation says that's what x is equal to, and then over 4. So I replaced x with lambda y. And now y looks like lambda squared times y over 4. So let's rewrite that as y equals lambda squared y over 4. Now, there's two ways that this could be true. There's two ways for this equation to be true. Case number 1. If y is equal to 0, then we are not allowed to divide it off, because you can't divide by 0. However, if y does equal 0, this equation is solved, right? If you could imagine that you have a 0 here and a 0 here, this equation would be true. You would get 0 equals 0. So one possibility is that y is equal to 0. Another possibility would be that y is not equal to 0. So possibility number 2, y does not equal 0. If y does not equal 0, then we are allowed to divide it off, which would essentially leave us with lambda squared over 4 is equal to 1. We can solve this equation for lambda, and we would find that lambda is equal to plus or minus 2. So we had two possibilities to make this equation true. Possibility 1, y is equal to 0. Possibility 2, y is not equal to 0, but lambda has to be either positive 2 or negative 2. And we're going to need to make sure that we check all three of these cases. The case where y is 0, the case where lambda is positive 2, and the case where lambda is negative 2. Okay, so I'm going to have to clean up my screen. Pause for a second while I clean things up. All right, so we have our possibilities, either y equals 0 or y does not equal 0, meaning lambda has to be positive 2 or lambda has to be negative 2. If that's true, then we can find the x values. So if x is equal to lambda times y and y is 0, then x would have to be 0. That just comes from plugging plugging y into this equation. X would have to be 0. Who cares what lambda is, right? X has to be 0 to make this true. And so we can check to see if this is our solution. Is x equals 0, y equals 0 the solution to this optimization problem? Well, the only way to know is to make sure that it satisfies all three equations in our system. We used the first two to find x and y, but we never used the third equation. And this is where we're going to use it. We'll plug x and y into this equation and make sure that it satisfies it. So x is 0, so we have 0 squared over 8. Y is also 0, so we have another 0 squared, this time over 2. And we want to know, does that satisfy the equation equal to 1? Well, the answer is absolutely not, because 0 does not equal 1. Which means the case where y equals 0 is not a solution. And solving systems like this can feel a little bit like you're doing a juggling act. But remember that if you're solving a system with three equations, you have to use all three of those equations. You have to make sure that whatever you pick to be your solution satisfies all three equations. And in this case, one of the possibilities we found did not work. Let's move on to our next possibility, the case where lambda equals positive 2. If lambda equals positive 2, then we know x has to be the same as 2y. And there's lots of values that we could make work here, depending on what x and y are. So rather than just trying to find x equals one number, y would have to be this other number, like let's say x is equal to 10, y would have to be 5. X is equal to 30, y would have to be 15. So there's infinitely many x, y combos that satisfy this. So what we'll do is plug that into the third equation. This third equation is going to make sure that our constraint is satisfied. So we'll have, instead of x, we'll write 2y squared over 8 plus y squared over 2 equals 1. Notice that this equation has one unknown, which means we can solve for y here. So we'll get 4y squared over 8 plus y squared over 2. 4 over 8 reduces to 1/2, so we get y squared over 2 plus y squared over 2. That gives us 1y squared. So y squared, and this whole time that equation was equal to 1, which means y has to be plus or minus 1. That would be our y values. And in order to find the corresponding x, we just go back to the statement we first started with that said x is equal to 2 times y. So x is equal to plus or minus 2. So from the case where lambda equals positive 2, we have 2 points. One, when x is equal to positive 2, y is equal to positive 1. When x is equal to negative 2, y is equal to negative 1. Now let's check the case where lambda is equal to negative 2. In this case, x would be equal to lambda times y, or negative 2 times y. And then we'd plug that into our constraint. And because we're squaring that x substitution in here, notice that we actually get the same exact thing that we had in the case where lambda equals positive 2. So these are identical, which means all the work that follows would be identical. So we know we're going to find y squared equals 1, or y equals plus or minus 1. And then we would go back to the x equation we started with, and we would say, okay, if y is equal to positive 1, then x needs to be negative 2. So let's write those points. If y is equal to positive 1, this time x would be negative 2. And if y is equal to negative 1, this time x would be positive 2, because of that equation we started with. So we have these 4 points, and based on the process of Lagrange multipliers, these 4 points are going to give us the maximum or the minimum of our function when we plug it in. So we need to plug each one of these 4 points into our function to find the max and the min. Now this function's pretty simple. F is equal to x times y, so we should be able to figure out the function value at each one of these points. If x is 2, y is 1, then the function is equal to 2. If x is negative 2, y is negative 1. Again, f is equal to 2. But in the case over here where x is negative 2, y is positive 1, the product comes out to be negative 2. And when x is positive 2, y is negative 1, the product comes out to be negative 2, which means the max of f, the max value of f, is equal to positive 2. The minimum value of f is equal to negative 2. All right, guys, this is the process of Lagrange multipliers. That's what this entire section is about. I'm going to stop this video because it's already gotten quite long, but I will upload another video for this section that shows you what to do in the case where you have 2 constraints. So I'll upload another example here shortly.